Hello and welcome back to our series on electrical and computer engineering. Tonight our conversation is about simplification. One thing that interesting electronic circuits share with one another, complexity. That's why we electrical engineers welcome any opportunity we get to simplify a circuit to reduce its level of complexity. Tonight we will be visiting the two simplest and most common of all the simplification methods, series simplification and parallel simplification. There is a caveat, however. When you're simplifying a circuit, don't overdo it. What do I mean by don't overdo it? Well, if you know in advance that for a certain resistor or inductor or component you're going to need the voltage and the current, the power, don't simplify that component. Leave it alone. With that caveat, we are ready. Let's begin. What simplifications? Elements in series we simplify, elements in parallel we also simplify. But what elements? Well, the usual resistors, inductors, capacitors, but also voltage sources and current sources. A word of caution to you all. Whatever you do, never simplify the element in which you need to compute the voltage and the current. How will we proceed with this video? First, I'll show you the how we do things, how we simplify, and then I will go into the demonstration of why the how works, the why. The why, how works the way it works. We begin with simplification of elements in series. Two elements of the same kind connected in series can be simplified. That is quite a statement. But of course it needs some clarifications. What do you mean by of the same kind? What I mean is two resistors or two inductors, etc. And exactly what is the meaning of simplified? Well, by simplify, I mean that the pair of elements can be replaced by a single element of the same kind, but with a value that you and I will compute. The key word here is replaced. You see, the original pair of element is removed, it goes out, and in comes the single equivalent replacement. In parallel, the same thing. Two elements of the same kind connected in parallel can be simplified. Again, the same kind means both are resistors, both are inductors, etc. And simplified means the usual. We'll remove the two elements in parallel and replace them by a single element whose value we will compute. Sometimes the simplification's computation is as simple as an addition. Let's see. To simplify several resistors in series, I'm not talking of two, I'm talking of 2, 3, 4, many of them in series, or several inductors in series as well, or several voltage sources in series. Of course, in this case, I need to take into account their polarities, as we shall see, or several capacitors in parallel, or several current sources in parallel, and in this case also we need to take into account their polarities. In each one of those 5 cases, we simply add their values together to obtain the value of the equivalent element that will replace them. Just an addition. Let's repeat. Resistors in series, inductors in series, capacitors in parallel, voltage sources in series, or current sources in parallel. In those cases, we just use addition as a computation technique to simplify elements. Can you be more specific? Absolutely. We add resistors in series, right? Let's take this as an example. You see the 3 resistors on the far right, R7, R8, and R9. They are in the same branch. Then according to what we show in our video on topology, those 3 resistors are in series. We add them together to find the equivalent resistor. We remove them free and replace them by a single resistor Req whose value is obtained according to that simple formula, R7 plus R8 plus R9. Observe, R7, R8, R9 are no more. They have been removed. They lost their identity. However, for R6, R4, 5, 3, 2, and 1, nothing has changed. Each one of the other resistors in the circuit, the ones that have preserved their identity, they see the same voltages and they see the same currents. In that sense, Req is equivalent to the original branch with the 3 resistors. And inductors? Yes, inductors in series we also can simplify the same way. Between nodes A and B, we have inductors L1, 2, 3, 4, n inductors. We can replace them by a single inductor with a value that is obtained just by addition, same way as with resistors in series. And can we simplify capacitors in series? Yes, but not this way. To add capacitors just with an addition, we need for them to be in parallel. In that case, as in the figure, we have n capacitors, C1, 2, 3, 4, n capacitors between nodes A and B. To find the equivalent, we just add them together, and that equivalent will replace the original ones. As simple as that. The equivalent capacitor is obtained as the addition of the capacitances of the original capacitors connected between nodes A and B. And what about voltage sources? You said we had to mind the polarities. Sure, look at this circuit. The sources 10 volts and 7 volts, they are in series because they are in the same branch, and that follows our definition for connection in series of the video on topology. However, they oppose one another. The 10 volt source is trying to push current in a clockwise direction, and the 7 volt source is trying to do the opposite. Of course, the 10 volts will win, and in the end what we have is a resulting voltage source of 10 minus 7, 3 volts only. That is how we simplify them. If they are pointing in the same direction, we add them up, and then we subtract all the sources that are pointing in the opposite direction in the same branch, in series, remember. Current sources too? Yes, but in parallel one. If we have several current sources in parallel, we add them up. Mind the polarities. Those two current sources are feeding a total current of IS1 plus IS2 to node A and sucking it out of node B. Both of them are equivalent to a single current source with a value IAQ that is the sum of the original current sources. If one of the sources had been pointing in the opposite direction, I would have had to subtract them. What about two current sources in series? No way. And I'm telling you why. Remember, when we put a 7 amps current source in a branch, that is a promise of us as engineers. That is a statement. You're saying, I will do whatever it takes to guarantee that the current in this branch is 7 amps. I will add all the electronic circuitry necessary to guarantee that the current in that branch is 7 amps. That is what that symbol means in a circuit. It's not a magic symbol. But when we go ahead and draw another current source of a different value in the same branch, let's say 5 amps, we are contradicting ourselves, because now we're saying, I will guarantee that the current in this branch is 5 amps. You and I remember that the branch current is the same all through every element. Otherwise, KCL would not hold true for that branch, which is impossible, right? It is us who contradict ourselves when we draw two current sources with different values in the same branch. Those are two equations. It would be as saying, my brother Joe is 2 years younger than me. But in the same phrase, oh, by the way, also my brother Joe is 5 years older than me. That is what you're saying. You're contradicting yourself when you do that. Don't do that. Don't do that. 5 and 7 in the same one? No way, absolutely not. There is only one case in which you can connect two current sources in the same branch. if they have the same value and the same polarity, which is redundant, of course. In that case, you simplify them because they are doing the same work as a single one. Now a few new definitions. Sometimes we prefer to specify elements not by their parameters, resistance, inductance, capacitance, but by their inverse. For a resistor, the inverse of the resistance is called the conductance. The units used to be called mhos, now are called Siemens, symbol uppercase S. For instance, the G of a capacitor that has a resistance of 1000 ohms is 0.001 Siemens. We say this is a 0.001 Siemens resistor, which is equivalent to saying this is a 1000 ohms resistor. For inductor, there is no established name for the inverse of the inductance, so we're going to make up one for this course. The inverse of the inductance is going to look like an upside down L, but that is in reality an uppercase Greek letter gamma. I'm going to call that the gamma of the inductor. That is the inverse of the inductance in Henry's inverses. And for the capacitor, same deal. There is no standard name for the inverse of the capacitance, but we're going to need it. And I thought, what is the opposite of capacity? That would be tightness, right? So I'm calling the tightness of a capacitor a little bit tongue-in-cheek by the inverse of the capacitance of a capacitor. The units, farads, inverses. The same way as I showed you a moment ago, that there are many times in which we achieve an equivalent just by adding together the parameters of the elements that we are combining, I will show you now that there is another group of cases in which we achieve equivalence by addition, not of the parameters, but of the inverses of the parameters. Let's see. To simplify several resistors in parallel, we add their inverses. To simplify several inductors in parallel, we add their inverses. Same with capacitors, but capacitors in series. In this case, we add their inverses. We simply add their inverses together. However, what we get is the inverse of the value of the equivalent element. So if we add together the conductances of the resistors in parallel, we get the conductance of the equivalent resistor. If we add together the gammas of several inductors in parallel, we get the gamma of the equivalent inductor. If we add together the tightnesses of several capacitors in series, mind you, we get the tightness of the equivalent capacitor. So you want some examples? Sure. To simplify several resistors in parallel, you add together their inverses and you get the inverse of the equivalent resistance. You know that, right? Let's say we have between nodes A and B resistors are 1, 2, 3, 4, n resistors in parallel. To compute the equivalent one, you add together the inverses and you get the inverse of the equivalent resistance, right? Like that. As simple as that. Or we could think of conductances. You add up the conductances G, 1, 2, 3, 4, N, and you get the conductance of the equivalent resistor. Again, for inductors too, yes, inductors in parallel, you can substitute them by a single equivalent inductor whose value is obtained like this. Add up the inverses of the original inductors in parallel and you get the inverse of the equivalent inductance that you need to connect between nodes A and B as a replacement. And finally, to simplify several capacitors in series, you just add their inverses and get the inverse of the equivalent capacitance, like this, right? There is a particular case that occurs very often, and renders a very useful formula when we have only two resistors in parallel, or two inductors in parallel, or two capacitors in series. In that case, the formula can be memorized very easily and applied even easier. For two resistors in parallel, R1 and R2, that is a formula that we use to obtain R equivalent. However, after a little bit of math manipulation, we obtain that equivalent resistance is obtained multiplying R1 times R2 and dividing by the sum of R1 plus R2. We can memorize that with words this way. To find the equivalent of two resistors in parallel, multiply them and divide by their sum. Easy to remember, right? Well, the same is true for two inductors in parallel or two capacitors in series. There is an immediate consequence of this simplified formula. What happens when the two resistors in parallel have exactly the same value? We apply the formula. Multiply R times R, divide by R plus R, and what do we get? We get R divided by 2. Conclusion. When we connect two resistors of the same value in parallel, the equivalent has half the value of either of the original ones. For instance, if you connect two 1000 ohm resistors in parallel, they are equivalent to a single resistor of 500 ohms. It's easy to demonstrate, and I leave that to you as an assignment, a homework, that if you connect n resistors of the same value R, each one of them, in parallel, they are equivalent to a smaller resistance value of R divided by N. For instance, if you connect 3 resistors of 1000 ohms each in parallel, the equivalent is a single resistor of 333 ohms. It's time for us to put some numbers to all the formulas. We are asked to find the equivalent resistance of all that group of resistors connected between the nodes on the left. The first thing we realize is that those 3 resistors are in series, so we can simplify them simply by adding them together. 4 and 5 is 9 and 3 is 12 ohms, right? We'll replace the 3 original resistors by this equivalent of 1. Now, 12 and 4 are obviously in parallel because they are in atomic branches connected to the same two true nodes. We can connect them in parallel. We'll replace them by a single equivalent resistor whose value is multiply 4 times 12 divided by 4 plus 12. 4 times 12 is 48. 4 plus 12 is 16. 48 divided by 16 is 3 ohms. So all of those 2 resistors are equivalent to a 3 ohm resistor, like this. Now, those 2 3 ohm resistors are in series with one another. We simplify them. Addition, 6 ohms. 6 and 6 are in parallel, and we know that 2 resistors of the same value in parallel are equivalent to 1 with half the value of either. So 6 and 6 in parallel are equivalent to a 3 ohm resistor, like so. 3 ohms. And finally, 4, 3, and 3 are in series. 4 and 3 is 7 and 3 is 10 ohms. That is the equivalent resistance of the whole group of resistors as seen by whatever circuitry we connect to those 2 nodes. Let's repeat this exercise now using the graphic calculator HP50G, whose emulator you can download for free from the internet as I describe in the following slide. What I have done is enter in the calculator all of the resistances starting from the left. You see 4, 3, 6, 3, 4, 4, 5, and 3. All of the numbers are there. When I punch plus, it will add up the 2 numbers at the bottom of the stack, combine them. So we begin. Add 5 with 3, that is 8. 8 and 4, that is 12. And that is the equivalent resistance of 4, 5, and 3 in series. And now that goes in parallel with 4 ohms, right? You see 12 in level 1 and 4 in level 2. We want to connect those two values in parallel. How? With this key, parallel. It will compute the parallel of level 1 with level 2. Punch that, 3 ohms. All of the circuit in the cloud is equivalent to 3 ohms. Now 3 ohms are in series with these other 3 ohms. They are in levels 1 and 2. I just add them together. 6 ohms is the equivalent resistance of everything that is now inside the cloud. That is in parallel with 6. So to connect in parallel those two resistors in levels 1 and 2, we punch again the F6 key and get the parallel is 3, and finally add them together and get that the total equivalent resistance of that group of resistors is 10 ohms, as we had computed before, a little bit more painfully. This is just to preempt the question I get every semester of where can I go and download the emulator of the HP50G that you are using in your videos. You can freeze the video and read what is in there. Now that we have seen how we simplify elements in series, how we simplify elements in parallel, it's time for us to justify why we do things that way. How is it that we add resistors in series? How is it that we add the inverses of resistors in parallel, etc.? Let's begin with answering a basic question. What does it mean to say that this is equivalent to that? Electric circuits have neither eyes nor ears. They only sense voltages and currents. As long as a given branch maintains the voltage between its true nodes and pulls the same current, changes inside the branch will not affect the rest of the circuit. The rest of the circuit will not realize that branch has changed. In that sense, the new branch, the modified branch, is equivalent to the original one, as far as the rest of the circuit is concerned, of course. Let's begin with resistors in series. How we find an equivalent resistor of two resistors in series. Take resistors R1 and R2 in series between nodes A and B. There is the branch current I, and that current I produces, according to Ohm's law, a voltage drop in resistor R1 and a voltage drop in resistor R2. Do you agree with me that the middle node is higher than B by V2, and that the top node A is higher than the middle node by V1? So A is higher than B by V2 plus V1, right? That is KVL. We can write it. VAB is V1 plus V2. Node A is higher than B by V1 plus V2. But who is V1? Well, V1 is the voltage produced by the current in the resistor according to Ohm's law. That voltage is proportional to the current according to R1. And something similar can be said about V2. Agree? So we substitute those two expressions in the formula at the top and say the total voltage drop in the branch is the sum. What can you tell me about that sum? Immediately you say that it has a common factor on the right hand side. It has I, which I can factor out like this. Let's go now to our equivalent scenario in which we have an equivalent resistor for us to find Req between nodes A and B. And we say it's equivalent. Why? Because with the same current I, it holds the same voltage VAB as the original pair of resistors. But the relationship between VAB and I in this new drawing follows Ohm's law and is given like that. VAB is Req times I. If you observe this equation and compare that with this other one, you come to only one conclusion, that Req has to be equal to this parenthesis down here. The value of the equivalent resistor has to be R1 plus R2, which is what we wanted to demonstrate. Let's do the same now for inductors in series. Two inductors in series, the branch current, that current depends on the voltage that appears in the inductor with a value of V1 and will create a voltage V2 in inductor L2. Again, we can write that A is higher than B by the sum of V1 plus V2. Who was V1? We memorized the behavior of an inductor as, repeat with me, V is L di dt. Absolutely. V1 is L1 di dt. And V2, the voltage in the second inductor is again V2 is L2 di dt. Both voltages depend on how quickly the current I is changing with time, how many amps per second it's changing, right? But if we substitute V1 and V2 in the expression on the top, we get that the voltage VAB is given by that expression. Again, what do you see there? You see an expression with a common factor on the right-hand side. You can factor it out like this, right? Absolutely. Let's move on now to the equivalent circuit scenario, this one. We have an equivalent inductor that we need to find REQ between nodes A and B. It will be equivalent if it pulls the same current I when the voltage is the same VAB. But you know the relationship between that VAB and I should be what? V is L di dt for an inductor. VAB is LEQ di dt. When you compare that expression to the one at the bottom on the left, you say LEQ has to be equal to the parenthesis on the left. LEQ is the sum of L1 and L2, which is what we wanted to demonstrate. Let's do a third and last one. Capacitors in parallel, right? Here are the two capacitors, C1 and C2 in parallel between nodes A and B. The voltage in each one of them, because they are in parallel, is the same VAB. We have seen that in a previous video. That voltage is responsible for the apparition of a current I1 in the first capacitor and I2 in the second capacitor. However, KCL tells us that a current will appear entering the branch through node A, current I, the total current. KCL says I is the sum of I1, the current in the first capacitor, plus I2, the current in the second capacitor. Who is I1? Who is I2? Anyone here remembers the behavior of a capacitor? I is C dV dt. The current in the capacitor is proportional to the change rate of the voltage, like this. That is the current I1. C1 dV dt. What voltage? VAB, the voltage in the capacitor. And something similar can be said about capacitor 2. Substitute that in the KCL equation on the top, and this is what you have. You know what I'm going to do? Factor out dV dt, like this. And I'll do exactly the same. Let me draw the equivalent circuit, CEQ, between nodes A and B. And by equivalent, I mean that when the voltage is VAB, the current is I, the same voltages and current that appeared in the original case. What is the relationship? Capacitor's behavior. I is C dV dt. For the equivalent one, I is CEQ dVAB dt. If you compare that equation to the one on the left and on the bottom, you conclude the equivalent capacitance value has to be the sum of C1 plus C2, and that is what we wanted to demonstrate. Now, what about the rest? Well, the other demonstrations are very similar, and I leave them up to you, the student, as an exercise. Now, if you're in my class, I want to remind you that demonstrations like these ones have the nasty habit of popping up as questions in quizzes, even in midterms. Especially those demonstrations
that do not appear in this video. You want more homework? Sure, a tiny homework for you, an easy one. How would you connect 3 capacitors with the same value, the same capacitance, 1,000 microfarads each one of them, in such a way that the equivalent capacitance is 1,500 microfarads? You tell me. If you're on a video, feel free to respond your answer. If you're in my class, just walk up to me and tell me what is your response at the end of the lecture. And that is all, my invisible friends. I hope you have profited from this video, and I hope to meet you again for our next video. Thank you very much.